My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about electromagnetic induction. Electromagnetic induction is the generation of an EMF in a coil when the current in adjacent coil changes. Also, we'll learn about mutual induction, self-induction. We'll learn about Faraday's and so many other things. So let's get started. Electromagnetic induction. Faraday's experiments. As you see, a coil of many turns is connected to a center zero galvanometer. A coil of many turns is connected to a center zero galvanometer. A magnet is held at rest close to one end of the coil, and no current is observed to flow in the coil. Okay, this happens when the magnet is stationary, is held at rest to one end of the coil. The magnet is moved, is pushed, plunged into the coil, is moved towards the coil, and the galvanometer needle swings to one side, indicating that a current is flowing in the coil. On removal of the magnet, when the magnet is moved away from the coil, the needle deflects in the opposite direction, indicating that a current, induced current, is flowing, but in the opposite direction. So we can summarize our observation as follows. The relative motion between a conductor and a magnetic field leads to a variation in the magnetic flux linked with magnetic flux intercepting the conductor, resulting in an EMF induced across the conductor. And now, talking about Faraday's laws. First law, the relative motion between a conductor and a magnetic field where there is a change in the magnetic flux linked with the conductor, induces an EMF. EMF is proportional to the rate of a change of the magnetic flux. This is the first equation. The induced EMF is directly proportional to the number of turns of the coil, number of turns on the coil. Turns which link the magnetic flux lines. So we can say EMF induced is proportional to the number of turns. This is the second equation. From the first and second equation, we can say EMF is proportional to N delta phi over delta T. Proportionality sign is replaced by equality, so we expect a constant. The constant is equal to 1. So EMF equals negative N delta phi over delta phi magnetic over delta T. You can observe something here, a negative sign. What does this negative sign indicate? The negative sign in the previous relation indicates that the direction, this is very important, it indicates Lenz's rule. It indicates that the direction of the induced EMF and thus direction of the induced current is opposing to the change producing the current, producing the induced current. Okay, as I said, this is Lenz's rule or Lenz's law. What about Lenz's law? And this is very important. It states that the induced current flows in a such direction, the induced current flows in a such direction to oppose the motion or to oppose the change producing the induced current. Experiment to explain Lenz's law. Okay, here in front of you we've got a coil of many turns connected to center zero galvanometer. A magnet is plunged into the coil with, north pole facing the coil. So, when the north pole of a magnet is pushed into the coil, the induced current in the coil flows in a direction such as to produce a north pole at the end of the coil facing the north pole of the magnet. Why? Okay, so as a repulsion force occurs, the repulsion force between the two like poles resists the approaching of the north pole, resists motion of the magnet. When the north pole is moved away, is pulled away from the coil, the direction of the induced current is reversed to produce a south pole. So when the north pole is pulled away from the coil, direction of the current, is reversed, and S pole is produced at the end of the coil facing the north pole of the magnet to oppose the removal of the south pole of the magnet. So in both cases, the direction of the current or the current flows in a direction such as to oppose motion. We've got something important to mention here. Lenz's law determines the direction of the induced current in a coil. Once again, it is used to determine the direction of the induced current, but in a coil. To determine the direction of the induced current in a wire, straight wire, we'll apply Fleming's right-hand rule. So once again, Lenz's law determines the direction of the induced current in a coil. Determination of the induced current in a straight wire, as I said, we'll use, Fleming's right-hand rule. Fleming's right-hand rule. What about it? It states that if the first 3 fingers of the right hand are held at right angles to each other, okay, with the forefinger in the direction of the field. So forefinger points in the direction of the field. Thumb, points in the direction of motion. What happens? The second finger points in the direction of the induced current. Second finger determines the direction of the induced current. And now let's compare between Fleming's left-hand rule and Fleming's right-hand rule. First of all, Fleming's left, it is applied when a current causes motion. We'll apply Fleming's left when a current causes motion. And we apply Fleming's right, when motion induces current. This is very important. Okay? In Fleming's left, we'll start with current. And when current is passed, what happens? Motion comes later. So it is used, Fleming left is used when current causes motion. But Fleming right, used when motion induces current. Used when motion induces current. Fleming's left determines the direction of motion of a current carrying a straight wire placed perpendicular to a magnetic field. So it is used to determine direction of motion. Fleming's right, used to determine direction of the induced current, okay, in a straight wire. And now talking about mutual induction. First of all, let's define mutual induction. It is the generation of an induced EMF in one circuit as a result of the change in the magnetic field of another nearby circuit. Let me say it again. It is the generation of an induced EMF in one circuit as a result of the change in the magnetic field of another nearby circuit. Now talking about the various methods, various ways for obtaining current by mutual induction. In front of you we've got two circuits, one which is the primary circuit, which consists of a battery, switch, rheostat, and a coil. And inside the coil there is a core, soft iron core, okay? And we've got a secondary circuit which consists of, yes, a coil of many turns, but wider coil connected to center zero galvanometer. We'll talk about the, yes, various methods to obtain current, induced current by mutual induction, okay? We'll take them one by one. One of them is to move the primary coil, energized one, into the secondary coil. Anyhow, we'll take it one by one. The primary circuit, as I said, consists of a cell, a switch, rheostat, and coil. Secondary circuit consists of a coil of wider area and greater number of turns, connected to a center zero galvanometer. There is an EMF induced in the secondary circuit in the instant that the current in the primary circuit is turned on and off without moving either coils. The current in the primary circuit is increased or decreased using the rheostat. The primary is turned on and either coil is moved towards or away from the other. Okay. Observations. The needle of the galvanometer swings to one particular side in the instant that. As a matter of fact, we've got 6 methods. In 3, yes, methods, the pointer swings in one particular side. Okay, we'll mention these 3 methods. Okay, when the current in the primary circuit is switched on, the pointer, yes, of the galvanometer swings to one particular side. When the current in the primary circuit is increased, also the needle will, yes, deflect in the same direction. When the energized means the switched on primary coil is pushed into the secondary coil. So the 3 ways are when the current in the primary is increased, when it's switching on the current in the primary circuit, when the switched on primary circuit is moved towards the secondary coil. In these 3 cases, the current induced in the secondary coil flows in an opposite direction, backward current we call it, to that of the current flowing in the primary circuit. That is to say, the EMF and thus the induced current opposes the increase in the magnetic field linking the secondary coil, because in the 3 cases there will be an increasing magnetic field linking with the secondary coil. And according to Lenz's rule, the current flows in a direction to oppose the change producing it. So it will oppose the increase in the magnetic flux. How? Yes, it will flow in a direction opposite to the current flowing in the primary circuit. The induced current takes the direction such as to weaken the magnetic field, linking the secondary when the field increases. Okay, the needle of the galvanometer swings to the opposite side in the instant that the current of the primary circuit is switched off. Current in the primary circuit is decreased. The energized primary coil is pulled away from the secondary coil. In these cases, the current induced in the secondary coil flows in the same direction as that of the current in the primary, so it is a forward current. The forward current opposes now the decrease in the magnetic field linking the secondary coil. The induced current flows in a way such as to strengthen the magnetic field linking the secondary coil when the field collapses. And now talking about increasing the EMF induced by mutual induction. Talking about how to increase the EMF induced by mutual induction. The induced EMF and thus the induced current can be increased by cutting more flux lines in a certain time. This can be achieved by, first of all, using a larger secondary coil of many turns, and by winding the coil on a soft iron core, placing the primary coil inside the secondary coil, strengthening the electromagnet by using iron core, by adding more turns, or by increasing the current flowing through the coil. Closing and opening the electromagnet circuit rapidly, thus cutting lines of the magnetic field faster. The EMF induced in the secondary coil is given, as a matter of fact, by the expression EMF in the secondary coil, EMF2, is directly proportional to the rate of change of the current in the primary coil. So it is proportional to delta I1 over delta T. So EMF is equal to minus M, delta I1 over delta T. Negative sign indicates Lenz's rule. Capital M indicates mutual inductance or coefficient of mutual induction. As I said, M is the N secondary delta phi magnetic over delta I1 means the current in the primary. Okay. And now we want to define mutual inductance or coefficient of mutual induction. EMF equals, yes, negative M delta I1 over delta T. So mutual inductance of two coils is the EMF induced in the secondary coil, EMF induced in the secondary coil, when the current in the primary primary coil, it changes at a rate of 1 ampere per second. Since EMF 2 is equal negative m delta I1 over delta t, so we can say volt is equal to Henry ampere over second. This is very important. So Henry is equivalent to, yes, second, volt, amperes, negative 1. And what about volt, amperes, negative 1? It is ohm. So Henry is equivalent to second times ohm, or ohm second. Henry is the SI unit of mutual inductance. Okay, so we need to define Henry according to the mutual induction. It is the mutual inductance of two coils. If an EMF of 1 volt is induced in the secondary coil, when the current in the primary it changes at a rate of 1 ampere per second. And now we've got a question. What's meant by the mutual inductance of two coils is 0.3 Henry. It means that an EMF of 0.3 volt is induced in the secondary coil when the current in the primary it changes at a rate of 1 ampere per second. So an EMF of 0.3 volt is induced in the secondary when the current in the primary changes at a rate of 1 ampere per second. And what about the factors affecting the mutual inductance of two coils? Okay, this is very important. First factor is the number of turns on each coil, the distance between the two coils, the type of core, volume of each coil. Okay. And now talking about another phenomenon called self-induction. What about it? It is the generation of an EMF in a coil, in a circuit, when the current flowing in the coil, when the current flowing or passing through a conductor is changed, the flux through the conductor is changed also. And this will induce an EMF in it. The self-induced EMF is given by the following relation. EMF is proportional to delta I1 over delta T. So EMF1 equals negative L delta I1 over delta T. And from Faraday's we can say EMF is equal to N delta phi magnetic over delta T, and it is also equal to L delta I over delta T, so we can say L is equal to N delta phi over delta I. Okay. SI unit of self-inductance is Henry. So Henry has two definitions, one according to mutual induction and the other according to self. So self-inductance of a coil is denoted by capital L, and it is the EMF induced in a coil when the current flowing through the coil changes at a rate of 1 ampere per second. And what about Henry? Definition of Henry according to self-induction. It is the inductance of a coil in which an EMF of 1 volt is induced. An EMF of 1 volt is induced when the current through the coil it changes at a rate of 1 ampere per second. Now demonstration of self-induction. How to demonstrate self-induction? In front of you we've got, yes, an electromagnet which consists of many turns connected to a battery, 6-volt battery, and a tapping key. Okay. The moment the circuit is broken, a small arc, okay, discharge appears at the switch contacts. Okay. The discharge, as a matter of fact, is caused by the large self-induced EMF as a result of the collapsing of the magnetic field around the electromagnet. And now, if a neon lamp is connected across the electromagnet and the experiment is repeated, what happens? Okay, the neon lamp flashes each time the switch is open. Okay. The discharge is caused by the large self-induced EMF as a result of the collapsing of the magnetic field around the electromagnet. The high EMF of self-induction is demonstrated. And now talking about the factors affecting self-inductance of a coil. First of all, number of turns of the coil, geometry of the coil, the type of the core, spacing of turns of the coil. And what about non-inductive coils? Non-inductive coils are coils which are doubly wound. Non-inductive coil is a coil whose wire is doubly wound. The wire is doubled back on itself before being coiled up. By these methods of winding, the coil has zero resultant magnetic field. And consequently, no self-induced EMF is set up when the current through the coil changes. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.